Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today we'll discuss basic PLC instructions. Our objective is to define the make, break, and output enable instructions common in most PLCs, as well as differentiate between electrical continuity as required by traditional hardwire relay-based ladder logic and logical continuity as required by most PLCs. Pay attention to this lecture, as it establishes fundamental ground rules about common PLC program instructions that, if misinterpreted, can be disastrous. This lecture is predicated on the assumption that viewers watch the Introduction to PLCs lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. Programmable logic controllers, or PLCs, are programmed using one of 5 accepted languages, where the choice of language depends upon the region where the PLC is employed. The languages include graphical means, like relay ladder logic diagrams, function block diagrams, sequential function charts, and textual methods like statement or instructions lists and structured text. A popular graphical method, ladder logic, mimics the schematics customarily employed in traditional hardwire relay-based ladder logic, including vertical upright power rails and rungs containing instructions in the process sequence. We'll start by discussing 2 input instructions, make and break, and 1 output instruction, output enable, central to programming a PLC using ladder logic. Often a PLC running a ladder logic program is summarized as 3 simple steps. First, the PLC examines the logical states of inputs. Then, it executes the ladder logic program in a sequential, rung-by-rung manner, and finally, delivers appropriate logical outputs. The amount of time a PLC takes to examine inputs, execute the program, and deliver outputs is known as scan time, where scan time is a function of a program's complexity and length. When programming a PLC, it is a recommended practice to minimize the number of instructions and rungs to minimize both the scan time and size of the stored program. Let's first discuss the 2 input instructions, make and break. Alternatively, these instructions are known as XIC, examine if closed, and XIO, examine if open. Another extremely helpful way of thinking about these instructions is if and if not. Before we begin, I will not apologize for the regrettable terms employed by some PLC manufacturers, since it was not I that coined them, but rather historical inertia has dragged these antiquated terms into modernity, quite like the human appendix in U.S. customary measurement units. They are stupid, and I don't like them any more than you do, but we're stuck with them, so we may as well get used to them. There are good ways, bad ways, and extremely convoluted and long-winded ways to differentiate between these 2 important PLC instructions, but I'm going to do my best to make this distinction clear and concise. I am asking you to jettison any baggage you may have with these concepts and just sit back and listen. Long story short, I don't care how you learn this topic. All I'm asking is that you learn it and don't forget it. The instructional methods as presented in this lecture have helped a number of my former students shortcut the nonsense and not second-guess themselves to death. First and foremost, the terms normally open and normally closed are used only to describe the electromechanical nature of real-world field input devices like switches and contacts, and should never, ever be used to describe instructions in a PLC. This push button is normally closed. This push button is normally open. In the deactivated state, as the name implies, the normally closed contact is closed, and the normally open contact is open. In the opposite activated state, the normally closed contact is held open, and the normally open contact is held closed. Similarly, this electromechanical relay has both normally closed and normally open associated contacts. Again, when the coil of the relay is in the de-energized state, the associated contacts are in their deactivated states. The normally closed contacts are closed, and the normally open contacts are open. When the relay coil is in the energized state, the associated contacts switch to their opposite activated state. The normally closed contact opens, and the normally open contacts close. When the coil is de-energized, the associated contacts revert to their deactivated state. These concepts should not be a surprise, and if they are, I am sending you all the way back to the beginning of the Basic Electronics 1 DC Circuit Analysis playlist to begin anew. Look me up again in 3 to 4 months once you've got this concept down. The fundamental confusion regarding the programmed instructions used by PLCs lies in the fact that the make and break symbols commonly used in PLC programs look like normally open and normally closed contacts, and people often mistakenly refer to them in this manner. I must reiterate, the terms normally open and normally closed are used only for the electromechanical nature of real-world field input devices like switches and contacts, and should never, ever be used to describe instructions in a PLC. This symbol is a make, examine if closed, XIC, or if instruction. This symbol is a break, examine if open, XIO, or if not instruction. There are a lot of confusing and tangled methods of defining and differentiating these instructions from each other and between the logical nature of PLC instructions and the electromechanical nature of field input devices, but I will cut straight to the point. PLCs look for logically asserted values, and the two instructions respond differently to the logical states of inputs. Let's first discuss how field devices deliver logical values to PLC input modules. A switch, by its nature, is a digital device in that it can be placed in one of two mutually exclusive binary states, either open or closed, never a little bit of both or halfway in between. When a switch between the source and the input is open, it does not deliver a voltage signal to the input and can be considered delivering a logical 0, low, or false. When a switch between the source and the input is closed, it does deliver a voltage signal to the input and be considered delivering a logical 1, high, or true. The terms 0, low, or false, and 1, high, or true are simply shorthand for the absence or presence of full pilot voltage. For a system using 24-volt DC control voltage, 0 volts would be considered logical 0, and full 24 volts DC would be considered logical 1. In a perfect world, there exists an impassable no man's land between these two digital states, considered invalid. However, in the real world, there's a bit of slop. For example, consider a PLC intended to operate using 24-volt DC that considers control signals between 0 and 5 volts a logical 0, and the values between 15 and 24 volts a logical 1. There still exists an invalid region between 5 and 15. However, the targets for logical 0 and logical 1 are a little larger now, allowing a degree of error due to real-world signal attenuation or poor connection. Different manufacturers may specify different acceptable ranges for logical 0 and 1. Consult the datasheet for your particular device of interest. Note the definitions of logical 0 and logical 1 are rooted in something called positive logic, in that the absence of voltage is a logical 0, and the presence of voltage is a logical 1. The same definition stood on its head could be used in something called negative logic, but this is stupid and confusing. Positive logic is the law, but that doesn't mean people don't disobey it. Be aware of this possibility. Now that we've established some pretty concrete expectations how field input devices deliver logical values to a PLC, let's discuss how the two instructions, make and break, respond to the received logical values. Pay attention because this is important, and I'm only going to say it like 1,000,000 times over the course of this lecture and the next and the next and the next. If a make instruction receives a logical 0 at the input, it does not allow logical continuity left to right. If a make instruction receives a logical 1 at the input, it does allow logical continuity from left to right. In contrast, if a break instruction receives a logical 0 at the input, it does allow logical continuity from left to right. If a break instruction receives a logical 1 at the input, it does not allow logical continuity from left to right. Put this in your pipe and smoke it. Note I'm using the term logical continuity as if a PLC program really established or interrupted current to an output, but this is an analogy only. However, using the graphical ladder logic programming method, it's still very helpful to think of it in this manner. One can think of the left upright rail as a source of logical 1s, i.e. full control voltage. And to logically energize an output on the right, a rung must deliver a logical 1 from left to right. Before we examine these input instructions in greater detail, we need to discuss the output enable, or OTE function. Luckily, this is easy because we're going to use positive logic. If an output receives a logical 0, it is not enabled. If an output receives a logical 1, it is enabled. The output enable instruction looks remarkably similar to a contactor coil and is often illustrated in a PLC program as a parenthesis enclosing the output of interest. Loads hooked to a PLC output include the coils of contactors, the solenoids of fluid power valves, and indicators like LEDs. Normally, a PLC delivers output signals via an electromechanical relay for AC or DC loads, a solid-state transistor exclusively for DC loads, or a triac or back-to-back reverse parallel SCR exclusively for AC loads. Let's assume we're dealing with electromechanical relay outputs since they're the easiest to understand. We'll discuss the peculiarities of the solid-state devices in other lectures. If an assigned output receives a logical 0 via the output enable instruction, the electromechanical relay coil is de-energized and the contact remains in the deactivated open state. Whatever load is attached to that contact is similarly de-energized. If an assigned output receives a logical 1 via the output enable instruction, the electromechanical relay coil is energized and the contact is actuated into the activated closed state. Whatever load is attached to that contact is similarly energized. Now that we've got a basic understanding and definition of the make, break, and output enable instructions, let's examine some simple PLC programs and see how they respond to various field input devices in various actuation states. Consider a 1 input, 1 output PLC using 24-volt DC control logic with a single field input device on input 1 and a pilot lamp on electromechanical relay output Q1. Note the electromechanical nature of the field input device is normally open, and I1 has been instantiated as a make instruction controlling output Q1. Consider the response of this system for two different scenarios. First, when the field input device is in its deactivated open state, and again when it is in its activated closed state. When the field input device is in its deactivated open state, input 1 is receiving a logical 0. Being a make instruction, this means the PLC program does not permit logical continuity from left to right, and the output remains de-energized. When the field input device is in its activated closed state, input 1 is receiving a logical 1. Being a make instruction, this means the PLC program does permit logical continuity from left to right, and the output is energized. The coil of electromechanical relay Q1 is energized, and its associated contacts close. The pilot lamp on output Q1 is energized. Note, some PLC manufacturers offer simulation utilities and the ability to remotely monitor a program in operation. A manufacturer may illustrate those conditions that permit logical continuity and alternate colors are bold, such as I have using pink, while keeping the instruction symbol the same. Let's step it up a notch by performing the same analysis on the same program with only a subtle difference. This time, the electromechanical nature of the field input device attached to input 1 is normally closed. Note the program is still written using a make instruction, despite the radically different electromechanical nature of the field input device. PLCs allow this flexibility, and I must again remind you that the electromechanical nature of the input device has absolutely nothing to do with how that particular input is logically instantiated in a PLC program. Again, let's consider the response of this system for two different scenarios. First, when the field input device is in its deactivated closed state, and again, when it's in its activated open state. When the field input device is in its deactivated closed state, input 1 is receiving a logical 1. Being a make instruction, this means the PLC program does permit logical continuity from left to right, and output Q1 is energized. The coil of electromechanical relay Q1 is energized, and its associated contacts close. The pilot lamp on Q1 illuminates. When the field input device is in its activated open state, input 1 is receiving a logical 0. Being a make instruction, this examines the PLC program does not permit logical continuity from left to right, and output Q1 is de-energized. Electromechanical relay Q1 opens, and the pilot lamp on Q1 is unilluminated. Although different field input devices were employed for these two different examples, notice how the make instruction responded consistently with the logical values as received by the input. If the make instruction receives a logical 0 at the input, it did not allow logical continuity from left to right. If the make instruction received a logical 1 at the input, it did allow logical continuity from left to right. The electromechanical nature of the field input device had nothing to do with how the make instruction responded. The make instruction only bases its decision off the logical value at the input. Most students don't have issues with the make instruction and its response to various input devices in various states, since it follows a predictable pattern that closely mimics electrical continuity in traditional hardwire relay-based ladder logic. The break instruction, however, is where folks get lost. Be warned, things are about to get weird. At risk of blowing your mind, let's now examine the break instruction and its response to various input devices in various actuation states. The break instruction, like the make instruction, does not take into account the electromechanical nature of the field input device attached to a particular input, but rather only bases its decision off the logical value at the input. The break instruction, however, is essentially the opposite of the make instruction in that it allows logical continuity when an input experiences a logical 0, whereas it disallows logical continuity when an input experiences a logical 1. Consider a normally open field input device attached to input 1, where input 1 has been instantiated in the PLC program as a break instruction controlling output Q1. Let's again consider the response of this system for two different scenarios. First, when the field input device is in its deactivated open state, and again when it's in its activated closed state. Again, note the program is written using a break instruction that allows logical continuity when an input experiences a logical 0 and disallows logical continuity when an input experiences a logical 1. When the field input device is in its deactivated open state, input 1 is receiving a logical 0. Being a break instruction, this means the PLC program does permit logical continuity from left to right, and Q1 is energized. The Q1 electromechanical relay closes, and the pilot lamp illuminates. When the field input device is in its activated closed state, input 1 is receiving a logical 1. Being a break instruction, this means the PLC program does not permit logical continuity from left to right, and output Q1 is de-energized. Electromechanical relay Q1 opens, and the pilot lamp turns off. The break instruction, in my experience, is one of the hardest scenarios for those just introduced to this topic to understand. Again, PLC program instructions have nothing to do with the electromechanical nature, normally open or normally closed, of the field input device. They simply respond to logical values as received by the inputs. As if that wasn't enough, let's now perform the same analysis on the same program with only a subtle difference. This time the field input device attached to input 1 is electromechanically normally closed by nature. Let's consider the response of the system for two different scenarios. First, when the field input device is in its deactivated closed state, and again, when it is in its activated open state. Again, note the field input device's electromechanical nature is normally closed, and the program is written using a break instruction that allows logical continuity when an input experiences a logical 0, and disallows logical continuity when an input experiences a logical 1. When the field input device is in its deactivated closed state, input 1 is receiving a logical 1. Being a break instruction, this means that the PLC program does not permit logical continuity from left to right, and the output remains de-energized. The pilot lamp is off. When the field input device is in its activated open state, input 1 is receiving a logical 0. Being a break instruction, this means the PLC program does permit logical continuity from left to right, and output Q1 is asserted. Electromechanical relay Q1 closes, and the pilot lamp illuminates. Again, note how the break instruction responded consistently with the logical values as received by the input, despite the differing electromechanical nature of the various field input devices. If the break instruction received a logical 0 at the input, it did allow logical continuity from left to right. If the break instruction received a logical 1 at the input, it did not allow logical continuity from left to right. The electromechanical nature of the field input has nothing to do with how the break instruction responds. the break instruction only bases its decision off the logical value at the input. Note that the flexibility offered by the make and break instruction set is one of the major advantages of PLC programs, and you simply must understand the differences between the two if you expect to proceed any further in this playlist. Too often the subtleties bounce off the skulls of many viewers when first introduced to this topic, so I consider it my highest duty to force it through their skulls with repeated aggressive hammering. In pursuit of this goal, consider all 8 possible combinations of electromechanical field input devices, normally open or normally closed, and various actuation states, deactivated or activated, examined with both instructions, make or break, and the resultant response. I'm going to walk you through this list once, and if at the end of this analysis you don't dig this on every level that I do, I'm asking that you please pause the lecture and stare at this list without blinking until you do so. Consider a normally open switch in the deactivated open state instantiated in a PLC program as a make instruction. In the deactivated open state, this switch delivers a logical 0 to the input, and the make instruction does not allow logical continuity, and the output is de-energized. Consider a normally open switch in the activated closed state, instantiated in a PLC program as a make instruction. In the activated closed state, this switch delivers a logical 1 to the input, and the make instruction does allow logical continuity, and the output is energized. Consider a normally closed switch in the deactivated closed state, instantiated in a PLC program as a make instruction. In the deactivated closed state, this switch delivers a logical 1 to the input, and the make instruction does allow logical continuity, and the output is energized. Consider a normally closed switch in the activated open state, instantiated in a PLC program as a make instruction. In the activated open state, this switch delivers a logical 0 to the input, and the make instruction does not allow logical continuity, and the output is de-energized. Now let's examine the same 4 situations using the break instruction. Consider a normally open switch in the deactivated open state, instantiated in a PLC program as a break instruction. In the deactivated open state, this switch delivers a logical 0 to the input, and the break instruction does allow logical continuity, and the output is energized. Consider a normally open switch in the activated closed state instantiated in a PLC program as a break instruction. In the activated closed state, this switch delivers a logical 1 to the input, and the break instruction does not allow logical continuity, and the output is de-energized. Consider a normally closed switch in the deactivated closed state instantiated in a PLC program as a break instruction. In the deactivated closed state, this switch delivers a logical 1 to the input, and the break instruction does not allow logical continuity, and the output is de-energized. Consider a normally closed switch in the activated open state instantiated in a PLC program as a break instruction. In the activated open state, this switch delivers a logical 0 to the input, and the break instruction does allow logical continuity, and the output is energized. As one might expect, the make and break instructions have opposite responses for the same scenarios, which is largely the point. You can do what you want with whatever you want to do it with as many times as you want to do it. PLCs offer this mind-blowing flexibility and more. Can you now dig this on every level that I do? Remember these 8 scenarios. Remember this table. Because one day, someone's going to take it away and expect you to know it on a quiz or an exam. Hint, hint. Moving on, let's now put the make, break, and output enable instruction to use in some example PLC programs. Here's a simple PLC program consisting of a make instruction examining input 1, controlling output Q1 on rung 1, and a break instruction also examining input 1, controlling output Q2 on rung 2. Let's assume input 1 is connected to a normally open field input device. Electromechanical relay outputs Q1 and Q2 both illuminate pilot lamps when energized. Let's examine the response of this system when the field input device is in its deactivated open state, and again when it is placed in the activated closed state. When the field input device is in its deactivated open state, input 1 is receiving a logical 0, being the absence of voltage. The make instruction in rung 1 does not allow logical continuity from left to right, and the Q1 coil is de-energized. The pilot lamp attached to output Q1 is off. In contrast, the break instruction in rung 2, examining the same input, does allow logical continuity from left to right, and the Q2 output coil is energized. The pilot lamp attached to output Q2 is on. When the field input device is placed in its activated closed state, input 1 receives a logical 1, being the presence of full voltage. The make instruction in rung 1 does allow logical continuity from left to right, and the Q1 coil is energized. The break instruction in rung 2, examining the same input, does not allow logical continuity from left to right, and the Q2 coil is de-energized. The pilot lamp attached to output Q1 is on. The pilot lamp attached to output Q2 is off. Do you see what this simple PLC program has already enabled us to do? We saved money. If we wanted to implement this same function using traditional hardwire relay-based ladder logic, it would necessitate more wires in addition to a more expensive and bulky mechanically interlocked switch package with a set of normally open and normally closed terminals. Note, as implemented using this flexible PLC, the field input device requires only a single set of terminals and contains fewer wires. In addition to these upfront savings, consider the long-term savings if you were ever asked to modify or upgrade this system. The PLC implementation could be reprogrammed far easier than a system using traditional hardwire relay-based ladder logic ever be physically rewired. Let's examine a 4-input, 4-output PLC making use of a different program. Note our schematic indicates there is a normally open maintain contact selector switch on input 1, a normally closed momentary contact red push button on input 2, a normally open momentary contact green push button on input 3, a normally open momentary contact yellow push button on input 4, and 4 pilot lamps on the 4 outputs. For the purposes of this introductory application, we won't be using all the field input devices nor all the outputs. However, we've wired them up anyways on the off chance the system ever needs to be reprogrammed to perform alternate functions. Again, the reprogrammable nature of a PLC is one of its major advantages. Let's put your newfound understanding of the make, break, and output enable instructions to the test, and say the PLC happens to be running this program. Note rung 1 is a series configuration of a make instruction examining I2 and another make instruction examining I3. Note inputs 1 and 4 aren't being employed in this program, nor are outputs 2 and 3. Pause the lecture and see if we can determine how this system will respond for 4 different scenarios. 1. When both the red and green push button are in their deactivated states. 2. When only the red push button on input 2 is activated. 3. When only the green push button on input 3 is activated. And 4. When both the red and green push button are activated. Here's a hint. Determine the logical values the field input devices attached to input 2 and input 3 send in their deactivated and activated states. Then consider how the instructions respond to these input conditions. Here's how the PLC responds to these 4 different scenarios. When no button is actuated, the normally closed red push button sends a logical 1 to input 2, and the normally open green push button sends a logical 0 to input 3. The make instruction examining input 2 permits logical continuity to input 3. However, the make instruction examining input 3 does not permit logical continuity onto the output. Output Q1 is de-energized. When only the red push button is actuated, the now open red push button sends a logical 0 to input 2, and the normally open green push button sends a logical 0 to input 3. The make instruction examining input 2 does not permit logical continuity to input 3, and we may as well stop our analysis right here, since regardless of the state of input 3, the output won't be energized. This shortcut isn't really that far from the truth how some PLCs operate. In order to minimize scan time, PLCs often turn back at the first locked door and only continue progress along a rung if logical continuity can be maintained. For this scenario, output Q1 is de-energized. When only the green push button is actuated, the normally closed red push button sends a logical 1 to input 2, and the now closed green push button sends a logical 1 to input 3. The make instruction examining input 2 permits logical continuity to input 3, and the make instruction examining input 3 permits logical continuity onto the output. Output Q1 is energized and the pilot lamp comes on. Note, as presently implemented, this PLC program does not maintain the last asserted state, and due to the momentary nature of the field input devices, the pilot light attached to output Q1 only comes on when the green push button attached to input 3, and only the green push button is actively being held closed. As soon as the operator releases the green push button, output Q1 is de-energized and the pilot lamp goes off. While this might be suitable for some applications, we'll examine holding circuits that maintain the last asserted state as implemented in PLCs using virtual relays and their associated instructions, software-generated holding circuits, and latching instructions in later lectures. Finally, when both buttons are actuated, the now open red push button sends a logical 0 to input 2, and the now closed green push button sends a logical 1 to input 3. As previously, the make instruction examining input 2 does not permit logical continuity to input 3, and we may as well stop our analysis right here, since regardless of the state of input 3, the output won't be energized. The point of this lengthy analysis being that the electromechanical nature, normally open or normally closed of the field input device, has absolutely nothing to do with how the make or break instruction responds to the logical values received at the PLC input. This flexibility is a major advantage of PLCs over traditional hardwire relay-based ladder logic, where one is often constrained to the unalterable electromechanical nature of a particular device. PLCs additionally are far more versatile since they can be quickly reprogrammed without the time-consuming necessity of physically rewiring it. This small system with only 4 inputs and 4 outputs could still be programmed and reprogrammed to perform a truly mind-boggling array of functions only limited by the time and creativity of the programmer and the memory capacity of the PLC. Alright, this about wraps up our brief introduction to the make, break, and output enable instructions common to most PLCs. I'll admit there is some truly dumb terminology employed by certain PLC manufacturers and subtle twists to wrap your mind around, but if you just get past these initial roadblocks, you'll find the advantages numerous. As already demonstrated with just these simple programs, we've shown that a PLC can be more flexible, save resources and time, and be easier to install, maintain, troubleshoot, modify, and upgrade in contrast to traditional hardwire relay-based ladder logic. We'll be making use of these instructions to implement PLC programs in later lectures. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.